Welcome to Grandpa's Late Nights. It's good to have you here again. Come in, settle down, let the day fall off your shoulders like a coat you don't need anymore. Wherever you are right now, tucked under a blanket, or lying flat with the lamp still burning low, or maybe on a train somewhere with your head against the cold window, I'm glad you found your way to me tonight. And before we begin, let me ask you the question I always ask, the one you don't have to answer out loud. Where in the world are you listening from? What time is it in your corner of the night? Somewhere it's raining. Somewhere it's snowing. Somewhere it's just very, very quiet. And that's the best kind of somewhere for what we're about to do. Now, look over at your nightstand. If there's a glass of water there, and if there isn't, imagine one, cool and still, catching a little of the light. I want to tell you something about it. Something true. Almost every single atom of hydrogen in that glass of water is nearly 14 billion years old. Not the glass. Not the water as water. The hydrogen itself. The tiny hydrogen that clings to the oxygen to make each drop wet. It was forged in the first 3 minutes of the universe, and it has never, ever been remade since. You are about to fall asleep beside something older than every star that has ever burned in the sky. Older than the sun. Older than the galaxy. And you can reach out and touch it. You could drink it. You probably will at some point before morning. That's what we're going to drift through tonight, you and I. The first 3 minutes. Not the first 3 minutes of your day, not the first 3 minutes of some film, the first 3 minutes of everything. And I'll try, as I always do, not to make it so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely on the way down. A fair trade, I'd say. So let me settle in beside you, the way a grandpa does on the edge of a bed, and let me tell you how the whole recipe of the universe got written in about the time it takes to soft boil an egg. There's a book. It's a small, gentle book, written back in 1977 by a physicist named Steven Weinberg, and he called it The First 3 Minutes. That title is where a lot of people first heard the idea that the beginning of the universe had a schedule to it. A clock. And it's a good title, because it turns out that the truly important cooking, the part where the universe decides what it's going to be made of, really did happen in about 3 minutes. The whole opening chapter, start to finish, unfolds in roughly the first 20 minutes. But the crucial stretch, the part where the real chemistry happens, is packed into just 3 of them. 3 minutes. That's the window. Hold that in your mind, softly, like a warm stone in your pocket. 3 minutes to make nearly all the hydrogen and helium that would ever exist. We'll come back to it again and again. Now, when I say the first 3 minutes, I need you to understand where we're counting from. Not from a sunrise, not from any morning. We're counting from the very beginning of time itself, the moment the people who study these things label, very simply, T equals 0. Time 0, the first tick of the first clock. Everything you have ever known or touched or loved comes after that moment. And tonight we're going to sit right down at the start of it and watch, slowly, patiently, as the universe takes its first few breaths. And here's the first thing that surprises people. At the very start, the universe was not dark. It was not cold and empty and full of stars the way you might picture space to be. It was the opposite. It was blindingly, impossibly bright. Picture a fog, but a fog made of pure light and energy and the tiniest particles, packed so densely and glowing so fiercely that it was hotter than the middle of any star that has ever existed. Not a candle, not a bonfire. A fog of fire filling all of space at once, everywhere, in every direction. That's where we begin. In the glow. There were no stars yet. Let that sink in gently. No stars. No planets. No moons. No oceans. No atoms even. Not a single finished atom anywhere. Just a smooth, even bath of radiation and matter, filling everything. The same everywhere you might have looked, if there had been eyes to look, which there weren't. It was uniform. It was calm in its own strange way, like a perfectly still pond that happens to be on fire, a smooth, hot, glowing everywhere at once. And this is the part I love most, the part that helps me sleep. Honestly, the early universe had no center. It had no edge. There was no single spot you could point to and say, there, that's where it all started, right there. Because it started everywhere, all at once. The whole thing was expanding, but not like a bomb going off, not like a firework bursting from one bright point out into the dark. That's the picture most people carry around, and it's not quite right. It was more like a loaf of bread rising in a warm oven. Think of raisin bread. As the dough rises, every raisin drifts away from every other raisin. Not because any one raisin is the center, but because the whole loaf is swelling everywhere at the same time. That's the universe. Every point moving away from every other point, no center, no edge, just a gentle, everywhere expansion. A rising loaf, warm and slow. I like that it wasn't an explosion. An explosion is loud and violent and frightening, and none of that belongs here, in the dark, with you halfway to sleep. This was a swelling, an unfolding, something opening up like a flower opens, only far too hot to hold. Now, the name. You've heard it 1,000 times, the Big Bang. And it's a funny thing, because the man who gave it that name didn't even believe in it. His name was Fred Hoyle, a British astronomer, and back in 1949 he was speaking on the radio, on the BBC, the British Broadcasting Corporation, and he used the phrase Big Bang almost to poke a little fun at the idea. He was skeptical of the whole theory. He doubted it. He preferred a different picture of the universe entirely. And yet the name he tossed off, half in jest, stuck like honey. It stuck so well that we still use it today, every single time we talk about the beginning. So the next time you hear Big Bang, you can smile and remember that it was coined by a man who didn't buy it on a radio broadcast in 1949. Names have a funny way of outliving the doubts that made them. And it's a slightly unfortunate name too, because, as we just said, it wasn't a bang. It wasn't loud. There was nothing outside it to hear it. It was a hot, silent, everywhere swelling of light. But the name is cozy in its own way now, worn smooth by decades of use, like an old word passed down through a family until nobody remembers who first said it. So let's go back, way back, to the very first slivers of time, and let me show you how fast things moved at the start. When I say the crucial part took 3 minutes, I want you to understand that before those 3 minutes. Whole ages of the universe had already come and gone in the blink of an eye. Fractions of a second in which everything changed. Here's one of them. 1/10,000th of a second in. That's about 10 microseconds. 10 millionths of a second. A length of time so short you cannot feel it, cannot imagine it. It's simply gone before it's begun. The universe had already cooled just enough for something wonderful to happen. The tiniest building blocks of matter, called quarks, were finally able to bind together. Before that instant, they couldn't. They were too hot, moving too wildly to hold on to one another. Let me slow down and tell you what a quark is, because we'll be spending the night with them. A quark is one of the smallest things there is. It's a building block, far, far smaller than an atom, smaller than the pieces that make up an atom, And in that first 10 millionth of a second, before they could bind, the quarks roamed completely free, unattached, swimming loose in a state so hot and so strange that physicists gave it a name almost as lovely as it is technical. They call it a quark, gluon plasma. Say it slowly. Quark, gluon plasma. A gluon is simply the little bit of glue that normally holds quarks together. That's really where the name comes from. Glue. And a plasma is just a very hot, glowing state of matter. The kind of thing you find in a flame or in the surface of the sun. So a quark, gluon plasma, is a fog so hot that even the glue can't make anything stick. The quarks and the glue just slosh around together, free and unbound, in a soup hotter than anything that would ever exist again. And then, at 10 microseconds, the universe cooled just past a certain point, and the soup thickened, and the glue caught, and the quarks locked together into the first real particles of ordinary matter. It's like the moment a warm liquid caramel finally cools enough to set. One moment it's flowing and formless, and the next it holds a shape. That's what happened to the very fabric of matter, in less time than it takes for light to cross a room. How hot are we talking at the moments that matter for our story? Well, in that first second, the numbers are so large that we stop measuring in ordinary degrees and start measuring in trillions and billions. Around the time the key events for building matter got going, the universe was somewhere near 10 billion degrees. 10 billion. I can't picture that, and neither can you, not really, and that's all right, you don't need to. Just know it's a heat with no comparison. A heat beside which the centre of the sun would feel like a cool spring morning. That's the furnace we're standing beside tonight. But it's a furnace at the far end of a very long hallway, 14 billion years away, so you can watch it in perfect safety, warm under your blanket. And here's the gentle rule that governs the whole story, the one thread that ties every single thing together tonight. As space expanded, it cooled. That's it. That's the whole engine. The bigger the universe got, the cooler it became, exactly the way a gas cools when you let it expand, the way the air rushing out of a bicycle pump or an aerosol can feel cold on your hand. When something spreads out, it cools down. And the universe has been spreading out and cooling down from that very first instant right up until this quiet moment you're lying in now. The entire history of the early universe is really just one long, patient, unbroken story of gentle cooling. From 10 billion degrees, down and down and down, one threshold at a time. I find that so soothing, honestly. The universe didn't rush. It couldn't. It just cooled steadily, and as it cooled it, crossed one threshold after another, and at each threshold something new became possible. First the quarks could bind, then, as we'll see, protons and neutrons could hold their shape. Then, later, the first true nuclei. Each step waited for the temperature to be just right, like a key turning in a lock, only when the metal has cooled enough to fit. No hurry, no panic, just cooling and unlocking, cooling and unlocking. That's the rhythm of the whole night. Now, before we go on and watch those first particles come together, let me pause here with you for just a moment, because I want to say a small thing, and then we'll drift right back into the fog. If you're finding this calm, if my voice and these old facts are helping to slow your mind down the way I hope they are, then a like and a subscribe genuinely helps this sleepy little channel keep going. I'm a small creator, just one old fellow with a microphone and a lot of quiet stories, and folks like you clicking that button is honestly what lets me keep leaving the porch light on, night after night. And to those of you who've already subscribed, thank you. Truly, you have no idea how much it means. So tell me, if you'd like, down in the comments, where in the world are you listening from tonight, and what time is it where you are? I love reading them in the morning, imagining all of you scattered across the dark side of the earth, drifting off together. That's all. No rush. Settle back in. Let's return to the beginning of everything. So, we left the universe at about 10 millionths of a second old, with the quarks just barely locking together into the first particles. Let's look closely at what they made, because it's a wonderfully simple recipe. Quarks are the tiny building blocks, and here is their most charming habit: they lock together in threes. 3 quarks, bound tight, make one single particle of ordinary matter. Not 2, not 4. 3, and there are different flavors of quark. That really is the word physicists use, flavors. But for tonight, for the whole of tonight, you only need 2 of them. 2 flavors. One is called the up quark, and the other is called the down quark. Up and down. That's all you need to remember, and honestly, that's most of the recipe for you and me and everything we've ever touched. Here's how it works. Take 2 up quarks and 1 down quark, lock them together in a little bundle of 3, and you have made a proton. 2 ups and a down, that's a proton, one of the 2 great particles that sit at the heart of every atom. Now take the other combination. Take 2 down quarks and 1 up quark, 2 downs and an up, lock those 3 together, and you've made a neutron. That's the neutron, the proton's quiet partner. Do you see how close they are? A proton is 2 up and 1 down. A neutron is 2 down and 1 up. The difference between them, the difference between the 2 building blocks of every nucleus in the universe, is just a single quark flipped from up to down. One little swap. That's the whole distance between a proton and a neutron. It's almost nothing. And yet, as we'll see tonight, that almost nothing quietly decides the recipe of the entire cosmos. The smallest differences, the ones you'd never notice, turning out to matter the most. There's something very comforting in that, I think. And this rule, 3 quarks to a particle, was already being obeyed within the first millionth of a second. The universe barely paused before it started assembling matter in threes. It's as though the pattern was there from almost the very first heartbeat, 3 by 3 by 3, building protons and neutrons out of the cooling fog. Now, what holds those 3 quarks together so tightly? There's a force for it, and it has the most honest, plain-spoken name in all of physics. They call it the strong force. That's it, just the strong force. And it earns the name, because it is the strongest of nature's 4 fundamental forces, stronger than gravity, stronger than the forces of magnetism and electricity, stronger than anything. It's the glue at the very heart of matter. It grabs those quarks, and it does not let go. Without the strong force, there'd be no protons, no neutrons, no nuclei, no atoms, no you. It's the tightest embrace in the universe, and it holds every particle in your body together right now, silently, without ever tiring. The strong force, strong by name, strongest by nature. Now here's a small, delicate detail, and I want you to hold it gently because we'll lean on it later. A neutron is very slightly heavier than a proton. Not by much, by about 0.14%, 0.14%. A whisper of extra weight. If a proton and a neutron were 2 apples in your hand, the difference would be far too small to feel, far too small to see. But it's there. The neutron carries just a hair more mass. And that tiny surplus of weight, that faint heaviness, quietly shapes the entire recipe of the cosmos, how much helium the universe could make, how much hydrogen was left over, all of it traces back, in part, to this feather's weight difference. The universe, it turns out, is built out of these almost nothings. A single flipped quark, a fraction of a percent of extra weight. Small things deciding everything. And that little bit of extra weight has a consequence, a rather poignant one. Because a neutron is heavier, a lone neutron, a neutron all by itself, out in the open, not tucked inside anything, is unstable. It doesn't last. Given enough time, a free neutron will quietly transform itself into a proton, shedding that little excess of weight to become the lighter, more settled particle. Nature, you see, generally finds it a touch easier to make the lighter of two things. Given the choice, matter tends to drift toward the lighter option, the way water drifts downhill. And the proton, being lighter, is the more restful state. So a neutron left alone will, in its own time, become a proton. But, and here's the tenderness of it, a neutron doesn't have to be alone. Tuck that same neutron inside a nucleus, nestle it in beside some protons and other neutrons, held snug by the strong force, and it becomes stable. It can rest there, safe, essentially forever. The very same particle that would slowly vanish out in the open can live an eternity if it's simply sheltered, held, kept in company. I find that lovely, and a little bit moving if I'm honest with you. A neutron on its own fades, a neutron among others endures. Even in the first minutes of the universe, before there was anyone to notice, matter already knew that things last longer when they're not alone. So how long does a lone neutron last, out there by itself? On average, about 15 minutes. 15 minutes before it quietly decays into a proton. And I want you to really sit with that number, because it's about to become one of the most important clocks in our whole story. 15 minutes. That's roughly how long a free neutron survives before it changes. It's a clock, a slow, reliable, ticking clock, and it was running perfectly on cue, right through those crucial first minutes of the universe. Tick, tick, every free neutron on a 15-minute fuse. Now, do you feel the tension quietly gathering here? Because here is the problem the young universe faced, and it's the problem that shapes everything that comes next. The universe needed its neutrons. It needed them to build the first elements, as we'll see very soon. You can't make helium without neutrons, you simply can't. But its neutrons were on a timer. Any neutron left out in the open, unsheltered, not yet tucked safely inside a nucleus, was slowly, one by one, disappearing, decaying away into protons, 15 minutes at a time. It's like having a bowl of snowflakes and needing to build something out of them before they melt. The clock is running. The neutrons are melting away. So the universe had to make its neutrons early, and it had to use them fast, before too many of them slipped away. It had to catch them and shelter them inside nuclei while there was still plenty to catch. This is why the timing matters so much. This is why 3 minutes, and not 3 hours, and not 3 days. There was a window, and the window was closing on its own, quietly, because the neutrons themselves would not wait. And that's the beautiful, gentle drama at the heart of tonight's story. Not an explosion, not a catastrophe, just a cooling fog, a ticking clock, and a race that had to be run before the melting was done. The universe had a deadline it did not choose. It was set by the neutron's own 15-minute patience, and by the slow cooling of everything, and by a fragile little stepping stone we haven't even met yet, a delicate thing that simply refused to form until the temperature was just right. But we'll come to that. There's no hurry. That's rather the whole point of the neutron, isn't it? That the ones who wait alone don't last, but the story itself can be told slowly, gently, with all the time in the world. Let me gather up what we've drifted through so far, softly, the way you'd gather a blanket up around your shoulders so you can carry it with you as you sink down further. We began at t=0, the very first tick of time, in a fog that wasn't dark but blindingly bright, a smooth, glowing, everywhere at once bath of light and matter, hotter than the heart of any star, with no centre and no edge, swelling like a loaf of raisin bread rising in a warm oven. We watched it cool, because that's the one thing it always does, expand and cool, gentle and relentless. We heard how Fred Hoyle, who didn't even believe the theory, gave it the name Big Bang on the radio in 1949, though it was never really a bang at all, only a silent swelling. Then we watched the first great setting point at about 10 millionths of a second, when the quark gluon plasma, that soup so hot even the glue couldn't stick, finally cooled enough for the quarks to lock together. 3 at a time, always 3. 2 ups and a down for a proton. 2 downs and an up for a neutron. One flipped quark between them, held tight by the strong force, the strongest force there is. And we found that faint, feather-light difference in weight, the neutron just a touch heavier. And how that whisper of extra mass sends a lonely neutron drifting slowly into a proton, unless it's sheltered inside a nucleus, where it can rest safe forever. 15 minutes, the free neutron's patience. A clock, ticking through the first minutes, setting the deadline for everything. That's where we are now. The universe is a cooling fog of protons and neutrons and light. 10 billion degrees and dropping, the neutron clock quietly running. It has all the pieces it needs to start building the first true elements. But it can't. Not yet. Because between where we are now and the first stepping stone of chemistry, there's a threshold that hasn't been crossed, a temperature that hasn't yet fallen far enough, and until it does, every attempt to build something is undone the instant it's made. There's a bottleneck coming, a patient, invisible gate that the whole universe has to wait in front of, cooling, while the neutrons quietly melt. And that waiting, that strange, tense, beautiful pause where the universe stands ready with all its ingredients, but simply cannot begin. That's exactly where we'll pick up the story, because the moment the gate finally opens, everything happens at once, in a rush, in a matter of minutes. The whole recipe of the cosmos, written in one quick, warm flood of creation. But not yet. For now, the fog just cools. The neutrons just wait. And so can you. There's nowhere to be, nothing to solve, no need to hold on to every word. The universe took its time getting here, and so can we. Let the numbers blur if they want to, let the names drift. The ideas will still be here, patient as a sheltered neutron, whenever you'd like to come back to them. Because somewhere in that cooling fog, 14 billion years ago, the hydrogen in the glass beside your bed was already waiting to be born. Not yet made. Not quite, but close. So close. Held in the pause before the gate. In just a moment of cosmic time, it would form, and then it would never change again. All the long way down through the ages to this quiet room, this late hour, wherever in the world you are. The oldest thing in the house, sitting there in the dark, keeping you company while you sleep. So let's stay here a little longer, in the warm fog before the beginning of chemistry, and let the universe finish its slow, patient cooling toward the threshold that changes everything. And here we are. Still in the fog, Still in that strange, patient, in-between moment where the universe has its ingredients, its protons, its neutrons, its vast ocean of light, but hasn't yet found a way to use them. The temperature is dropping. The fog is thinning, degree by degree by degree. And something is about to happen. It happens at about 1 second old. 1 second, not 3 minutes, not 20. 1 single second after the beginning of time, a quiet transformation occurs, one that most of us never hear about because it doesn't make for dramatic pictures. There's no flash, no collision, no visible event. But it is, in its own way, one of the most decisive moments in all of cosmic history. Because at roughly 1 second in, the universe makes a choice it cannot unmake. It freezes the ratio of neutrons to protons. And that ratio, that quiet, abstract little fraction, decides nearly everything that comes next. Let's sit with it. At 1 second old, the universe is still extraordinarily hot. We're talking about 10 billion degrees. That number is almost too large to feel, so try this. The core of our sun right now, the blazing nuclear furnace at its very center, is around 15 million degrees. And the universe at 1 second old was 10 billion. About 700 times hotter than the center of the sun. Every particle is moving at almost unimaginable speed. And in that frantic, dense heat, protons and neutrons are constantly converting back and forth into each other. Like a frenzied exchange, a proton absorbs a particle and becomes a neutron emits a particle and becomes a proton, over and over, so fast that no steady count can be taken. But at around 1 second, that frantic exchange slows, and then, essentially, stops. What stops it is cooling. As the universe expands and cools, the particles and the tiny ghostly messengers that carry the signal for those conversions, particles called neutrinos, which we'll meet properly in just a moment, begin to lose their grip on each other. The reactions that let protons become neutrons and neutrons become protons start to cost more energy than is available. The trading halts. The ratio locks. And at the moment it locks, for every 1 neutron, there are about 6 protons, 1 to 6, a quiet imbalance held still as the universe continues to cool. The reason the ratio is unequal, the reason protons come out ahead, is almost disarmingly simple. Neutrons are heavier than protons, just barely, about 0.1% heavier, but that's enough. And nature, in its most basic expression, tends to favor the lighter option when it can. In that frantic early heat, when particles were converting back and forth freely, the balance naturally leaned toward the lighter particle. So protons were always slightly more common, and when the exchange froze, that preference was captured, like an insect held in amber. 1 to 6, 1 neutron for every 6 protons. But here's something beautiful. That isn't the final number. Because neutrons, when left free, not sheltered inside a nucleus, just floating alone in space, don't last forever. A free neutron decays. It transforms, slowly but steadily, into a proton, releasing a couple of smaller particles in the process. This is not a catastrophic collapse. It's quiet, gradual, unhurried. But it happens, and its average lifetime is about 15 minutes. Not millions of years, not thousands. 15 minutes, roughly the time it takes to brew a pot of tea. So the clock is ticking. From the moment the neutron-to-proton ratio freezes at 1 to 6, the neutrons begin a slow, patient disappearing act. Some become protons. The ratio shifts. And by the time the universe finally reaches the right conditions to actually build its first proper element, a few minutes later, Around 3 minutes in, the ratio has gently tilted further. Now there is about 1 neutron for every 7 protons. 1 to 7. This matters enormously. Everything that comes next flows from this single fraction. Now, let's talk about the neutrinos, because at almost exactly the same moment the neutron-to-proton ratio locks, around 1 second in, something else remarkable happens, quietly, without fanfare. The neutrinos let go. Neutrinos are extraordinary particles. They're extraordinarily light, so light that for a long time physicists weren't sure they had any mass at all. They carry no electric charge. They interact with ordinary matter almost not at all. A beam of neutrinos could pass through a wall of lead 1 light year thick, a light year of lead, and most of them would come out the other side without touching a thing. Right now, as you lie there, trillions of neutrinos are passing through your body every single second. Through the mattress, through the floor, through the earth itself, barely noticing any of it. In the very young universe, though, things were different. When the universe was dense enough and hot enough, neutrinos did interact. They were bound into the frantic dance of particles, part of the constant back and forth. But at around 1 second, when the universe had expanded and cooled just enough, they crossed a threshold, a point where even they could no longer keep pace with the dance. And they decoupled. That word, decoupled, is gently technical. It means they stopped interacting. They drifted free. The rest of the universe, the protons, the neutrons, the photons of light, carried on without them. And the neutrinos just travelled outward, in every direction, at nearly the speed of light, through all of space, unconcerned, unbothered, for 14 billion years. And here is the part that takes a moment to absorb. They're still here, those neutrinos from the universe's first second, those ancient, ghostly relics, fill the entire cosmos today, just as they did then. A vast, invisible sea. They pass through you constantly, those exact ancient particles, barely older than the oldest thing the universe ever made. We call this the cosmic neutrino background, and it exists at a temperature of about 1.95 degrees above absolute zero. The coldest whisper of the universe's very first second, still drifting through your room right now, unaware of you, undetectable without the most extraordinary instruments. Just passing through. Quietly, persistently, patient as anything. At just about the same moment the neutrinos were drifting free, another brief drama was playing out in the young universe. One that lasted only a short while and left a lasting mark. Electrons and their antimatter counterparts, called positrons, were still being created and annihilated in pairs. Matter and antimatter, flickering in and out of existence in the intense heat, cancelling each other out in tiny flashes of pure light. But as the universe cooled below a certain threshold, the heat was no longer sufficient to keep making new electron-positron pairs fast enough to replace the ones being lost. And so, gradually, they annihilated each other, pair by pair, in a last warm surge. When it was over, the tiny excess of ordinary electrons that had existed all along survived, because there was nothing left to pair with. And all that energy, all the energy from all those annihilations, was released not as particles, but as light, as photons, and that energy poured into the surrounding bath of radiation. It warmed the light. Not by much, but precisely, predictably, by a factor that physicists can calculate exactly. The photons ended up a little warmer than the neutrinos, because the photons received that last gift of energy from the electron-positron annihilation. The neutrinos, having already decoupled, missed out on it. And so today the cosmic background radiation sits at 2.725 degrees above absolute zero, while the cosmic neutrino background sits at 1.95 degrees. Two temperatures, two ancient relics of two different moments in the universe's first second, still measurable, still there. So the count stands. 10 billion degrees, 1 second in. 1 neutron for every 6 protons, ratio frozen. Neutrinos drifting free, already on their way across eternity. Electrons and positrons winking out in a final warm flash. And the ratio quietly drifting toward 1 to 7 as the free neutrons tick slowly down through their 15-minute lifetimes. The universe is cooling. And something is about to try to form. The very first step toward making any element at all, is the simplest step you can imagine. Take 1 proton. Take 1 neutron. Press them gently together. What you get is called deuterium. Deuterium is hydrogen, but heavier. Normal hydrogen is just a single proton, alone, with an electron orbiting it, the simplest atom in the universe. Deuterium keeps that proton, adds a neutron to its nucleus, and becomes what chemists sometimes call heavy hydrogen. It behaves almost exactly like regular hydrogen in most circumstances. It burns when you light it. It bonds with oxygen to make water. But it carries a little extra weight in its heart. And deuterium is not just a curiosity, it is the only door into the rest of chemistry. Nothing heavier can form without it. Not helium, not lithium, not any element above hydrogen in the periodic table. Because all the reactions that build larger nuclei have to pass through deuterium on the way. It is the essential stepping stone, the first rung of the only ladder that exists. And if deuterium can't form, if it's destroyed as fast as it's made, then the whole story stops here. The universe remains a sea of single protons and neutrons forever, and nothing more interesting ever happens. For a while, for those first 2 or 3 minutes, that is almost exactly what happens. Here's why. For deuterium to survive, the neutron and proton that form it have to stay together. They're held by a bond, not as strong as the bonds that hold the larger nuclei together, but real and meaningful. The energy it takes to break a deuteron apart is about 2.2 million electron volts, a specific, measured number, a gentle but genuine grip. But the early universe is filled with photons, particles of light. And there are not just a lot of them, there is a number that sounds nearly impossible when you hear it. For every single particle of ordinary matter in the early universe, there are roughly 1.5 billion particles of light. 1 particle of matter. 1.5 billion photons. This ratio, this extraordinary lopsidedness, has a name, the baryon to photon ratio. And it means that even when the photons don't have quite enough energy to break a bond on their own, sheer numbers overwhelm the situation. There are so many photons crowding around every newly formed deuteron that statistically one of them is always energetic enough to shatter the bond. Every time a proton and a neutron drift together and form a deuteron, a photon finds it, almost immediately, and breaks it apart. The proton and neutron drift free again. And wait, this is the deuterium bottleneck. It is not a barrier of force. No cosmic hand is pressing the nuclei apart. It is simply a barrier of abundance. Too much light, moving too fast, breaking things before they can hold. The universe wants to make deuterium. Protons and neutrons collide constantly. Bonds form, and then immediately shatter. And so the neutrons wait, ticking down their 15-minute lifetimes, slowly becoming protons as the universe cools and cools and the ratio drifts from 1 in 6 to 1 in 7. There is something almost contemplative about it, if you let yourself feel it. All the ingredients for the first real element, present, ready, colliding constantly. And yet, Nothing holding. Like trying to build something on a beach with the tide coming in, except the tide is 1 billion photons for every grain of sand. But the universe is patient, and the temperature is falling. Somewhere around 3 minutes after the beginning, the 3 minutes that give Weinberg's book its title, the 3 minutes that are the entire focus of this long, quiet night together. The temperature finally drops far enough. It settles to around 1 billion degrees, and at 1 billion degrees, something changes. The photons are still there, 1.5 billion of them for every matter particle. But now their energy has dropped just enough. The average photon, the typical photon in the universe at this moment, no longer carries quite enough punch to break a newly formed deuteron apart. The bond of 2.2 million electron volts is finally, just barely, strong enough to hold. A deuteron forms, and this time it stays. And then another one forms, and stays. And another, and another. The gate opens. That sudden shift, the moment the deuterium bottleneck breaks, is not gradual. It happens quickly, by cosmic standards. Once the temperature drops far enough, deuterium begins to accumulate faster than the photons can destroy it. The stepping stone appears, and the reactions that have been waiting patiently for those 3 minutes begin cascading forward. From deuterium, the universe builds, quickly, urgently, because the window is not going to stay open long. The clock from the neutron's 15-minute lifetime is still running. The universe is still cooling, still expanding, still thinning the soup of particles that makes fusion possible. There are only a few minutes left to do what needs to be done. But for now, for this one bright, brief, extraordinary moment, the first chemistry in the history of the universe is underway. The smallest atom, one proton alone, has found its partner, held on, and become something new, something more. Deuterium, heavy hydrogen. The threshold crossed. And the question that's been waiting, patient and quiet, behind everything we've talked about tonight, the question of what the universe actually makes once the gate is open, what element floods into being in those few precious remaining minutes, and how much of it the cosmos produces, and how we know that question is just on the other side of where we are now. But first, a quiet moment. Because this one felt right to pause in. You know, after years of a racing mind at bedtime, the kind that rehearses the day and rewrites conversations and checks the time every 20 minutes, deep and genuinely restful sleep felt like something other people had. Not me. But it changed, real change. The kind where you wake up and the room feels different, lighter, like something was returned to you. Learning comes easier after that kind of sleep. Energy doesn't have to be manufactured with coffee. The mind just does what it's supposed to do, without the friction. If that sounds like something worth knowing more about, the link in the pinned comments has the exact system that made it possible for me. Now, where were we? Right, the gate has opened. The deuterium is holding. And we were just about to find out what happens next, in the few bright minutes after the bottleneck breaks, when the universe finally gets to do what it's been preparing for all this time. Because here's where it gets genuinely wondrous. The deuterium that forms in those first moments doesn't just sit there, it reacts. Almost immediately, deuterium nuclei begin colliding with each other, and with the free protons and neutrons still drifting around, and the collisions produce something new. Something the universe has been building toward since the very beginning, through all the waiting and the cooling and the slow drift of the ratio from 1 in 6 to 1 in 7. The universe is about to make helium, and it is going to make a lot of it. Very quickly. In a rush of nuclear chemistry that lasts only a matter of minutes, the young cosmos will set the proportions of its two most abundant elements for the next 14 billion years, a recipe written in fire and locked in place before a single star existed. The neutrons that survived, the ones that didn't decay during the long bottleneck, the ones that made it through, are about to find their permanent home. Locked away, two by two, into the most stable light nucleus that nature knows how to make. And that stability, that remarkable, almost excessive stability of the nucleus they're about to enter, is the reason the universe settled on the fractions it did. The reason, when we look out at the oldest, most pristine gas clouds in the universe today, we find almost exactly the same proportions we can calculate from first principles, from knowing just the neutron-to-proton ratio and the temperature at which the bottleneck broke. But let's not get ahead of the story. The helium is still forming, the minutes are still ticking, the neutrons are still racing their own clock. And somewhere, in a quiet way, all of this is still happening to you. The hydrogen in the water beside your bed, the hydrogen that was made in these very minutes we're describing, passed through the deuterium phase on its way to existence. Most of it didn't stay deuterium, of course. Most of the deuterium that formed went on to react, to become helium or something else, before the bottleneck closed again. But the deuterium that didn't react, the small fraction that survived unreacted until the universe cooled too far for fusion, became a permanent relic. Frozen in place. Preserved across the entire age of the cosmos, through the birth of galaxies, through the ignition of stars, through billions of years of nuclear chemistry inside stellar furnaces. Still here. And here is something that takes a moment to absorb. Deuterium is not made inside stars, not in any meaningful way. It's only destroyed there, burned up in the fierce heat of stellar cores. So every deuterium atom that exists in the universe today, in the oceans, in your body, in ancient gas clouds, billions of light years away, is a genuine relic, untouched, made in the first few minutes of time, and never replenished. In that sense, deuterium is perhaps the most perfectly ancient thing that exists. It carries the fingerprint of the bottleneck in its very survival. And because it's so fragile, so sensitive to the conditions of that early universe, the amount of deuterium we can measure today tells cosmologists, with remarkable precision, exactly how much ordinary matter the universe contains, not dark matter, not dark energy, ordinary matter, the stuff made of protons and neutrons, the stuff you and I are made of. Deuterium is a baryometer, a scale, calibrated in the first 3 minutes that we're still reading today. And right now, in this cool, quiet night, a small trace of deuterium exists in the water beside your bed. In every molecule of water, statistically, 1 in every few thousand hydrogen atoms is actually deuterium, the heavy version, with the extra neutron in its heart. A genuine, unbroken relic of the universe's first minutes, dissolved in something as ordinary as a glass of water. The universe is full of these quiet marvels, hiding in plain sight, patient, waiting for someone to look closely enough to notice them. And in just a moment, after the cascade of reactions unleashed when the bottleneck broke, after the neutrons find their shelter and the first real element beyond hydrogen floods into existence, we'll see how the universe wrote those proportions in a way that could be read billions of years later. Like a letter from the beginning of time, but let the fog settle a little, if you'd like. There's no rush. The deuterium formed 3 minutes after the Big Bang and has been waiting patiently for 14 billion years. It can wait a moment longer while you breathe and drift, and let the numbers soften at the edges. 1 to 7, the neutrons and protons. 1 billion degrees, the temperature at the threshold. 2.2 million electron volts, the grip of the deuteron. 15 minutes, the lifetime of a free neutron, tick-tick ticking through those first fragile minutes. These are not numbers to memorize. They're just the quiet, specific textures of the story, the way real things have real measurements. And the measurements are beautiful in their precision, and you don't have to hold them to feel the shape of what they describe. The shape is this: the universe spent its first 3 minutes in a kind of creative tension. Ingredients ready, clock running. A gate that wouldn't open until the temperature said so. And when it finally opened, everything happened at once. In a flood of reactions that lasted only minutes, and the entire recipe of the cosmos was set. Everything after that, every star, every planet, every ocean, every sleeping person lying in a quiet room somewhere in the world tonight, is a long, patient elaboration on what happened in those 3 minutes. And we're right at the edge of it now. The gate is open. The deuterium is holding. The neutrons are finding their partners. The helium is about to arrive. And there was something else happening, quietly, around that same first second, easy to miss, because the universe wasn't announcing it. No flash, no explosion, just a quiet parting of ways. Neutrinos had been part of the early mix all along. These are extraordinary particles, nearly massless, extraordinarily shy, able to pass through most matter as if it simply weren't there. In the hot, dense first second, they'd been talking to the rest of the particles, interacting, exchanging, keeping company the way particles do when everything is packed close and the temperature is enormously high. But at around 1 second old, the universe had spread thin enough and cooled enough that those conversations simply ended. The neutrinos decoupled, walked away from the party, and since that moment, every moment since, without pause, they have been drifting through everything. Through the earth. Through you. Right now, as you lie there. Trillions of them every second, sliding through solid matter as if it weren't there at all. As if you weren't there. They've been doing this for nearly 14 billion years, and they're still out there. A faint sea, a cosmic neutrino background, hovering today at about 1.95 degrees above absolute zero, just barely above the coldest temperature the universe allows, barely more than nothing. But real. They are older than any atom. They were already free before the first hydrogen nucleus found a partner. And something happened shortly after they left that drew a permanent line between them and the light. The electrons and positrons, ordinary electrons and their antimatter twins, had been annihilating each other throughout the early heat. Matter and antimatter meeting and converting into photons, into light, a process that had been quietly running since long before the first second. But as the universe cooled through those first few seconds, the last great surge of electron-positron annihilation completed itself. They met in their final enormous numbers, flashed into photons, and were gone. And those photons gently warmed the radiation around them. Just a little, just enough. The neutrinos had already left by then. They missed it. So the photon bath ended up slightly warmer than the neutrino sea and has stayed that way ever since. The cosmic microwave background, the glow of the early universe we can measure today, sits at 2.725 degrees. The cosmic neutrino background at 1.95. The same beginning, the same first minutes, but one bath warmer than the other, divided by that single last annihilation. It's a small difference, but the universe keeps it, faithfully, all the way to now. So, by about 1 second in, the accounts were settling. The neutron-to-proton ratio was frozen close to 1:6, and the slow tick of neutron decay was already beginning to nudge it toward 1:7. The neutrinos had departed into their long, solitary journey. The photons had received their small inheritance of warmth, and the leftover matter, protons and neutrons, in their unequal numbers, was waiting for the temperature to fall far enough to allow the next step, and the next step was deuterium. 1 proton, 1 neutron, held together by about 2.2 million electron volts of binding energy. A modest grip, really, tight enough to hold, but barely. Tight enough to be shattered by a sufficiently energetic photon, and in those first few minutes, the photons were still energetic enough to shatter it. Here is what makes the deuterium bottleneck so quietly remarkable. It wasn't that the ingredients were missing. Protons were everywhere. Neutrons were drifting through the mix in their steady ratio, 1 for every 6 or 7 protons. Ready to pair, they were even finding each other, forming these fragile little deuterons, these tiny partnerships of 1 and 1. But the light kept breaking them apart. Not because each photon was particularly powerful, because there were so many of them. For every single particle of ordinary matter in the universe, there were over 1 billion particles of light. 1 billion to 1. The ratio is so lopsided it hardly seems real, but it meant that even though most individual photons were too weak to break a deuteron, there were simply so many in line that each new deuteron barely had a moment to exist before one found it. 1 billion patient claimants, each taking a turn at a very fragile thing. And so the universe waited. Not 1 second, not 2. 3 full minutes. 2 of those minutes spent waiting, after the protons and neutrons had already settled into their final ratio, because the light was still too thick, still too bright, still just barely too energetic to let the story continue. At about 3 minutes old, the temperature fell to roughly 1 billion degrees, and at 1 billion degrees the balance tipped. The photons still outnumbered the particles by more than 1 billion to 1 that hadn't changed, wouldn't change for a long time. But they had cooled just enough, dropped just below the energy needed to break the deuteron bond with any reliability. And the deuterium held, and stayed, and the cascade began. But before we follow it, before we watch the helium flood in, there is one more quiet thing to say about deuterium, because it is one of the stranger facts in all of cosmology, and it deserves a moment. Deuterium is the most delicate relic of those first minutes. Stars destroy it. Every star that has ever burned has taken in deuterium and broken it down, fused it onward into heavier things, consumed it without ever making more. So the amount of deuterium in the universe has only fallen, never risen, since those 3 minutes ended. Which means that whatever deuterium you find in an old, pristine gas cloud, one that has never been processed by a star, is essentially original, a direct leftover from the bottleneck, and the amount of it is extraordinarily sensitive. Change the total amount of ordinary matter in the early universe by even a modest factor, and the surviving deuterium would shift dramatically. Too much matter, and almost all the deuterium gets burned onward to helium in those 3 minutes. Too little, and more survives. So astronomers measure the deuterium in the oldest, most chemically untouched gas they can find, clouds at the very edge of what telescopes can reach, relics of a universe not yet enriched by generations of stars, and they read from it, like reading the rings of a very old tree, the total amount of ordinary matter the universe contains. A baryometer, a cosmic scale that works by counting the leftovers of a 3-minute fire, and the number it gives agrees to remarkable precision with numbers that come from an entirely different direction. Two independent measurements across completely different physics pointing to the same answer. The universe, it turns out, keeps its receipts. Now, there is something worth mentioning here, one element the first minutes tried to make. A quantity so small it barely seems worth counting, and yet the leftovers of it don't quite add up. Astronomers have looked at the oldest stars, stars born close to the beginning, and found less of it than the recipe says should be there. The number the theory gives and the number the stars show are off. Not by a little, by a factor of about 3. It's been sitting there, politely, for decades. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But here's where it gets strange. Lithium, the lightest metal, element number 3 on the periodic table. The same element that keeps your phone alive, made in those 3 minutes in quantities so small, a few atoms for every 10 billion hydrogen atoms, that you'd expect the count to be simple. Tidy, obvious. And yet it isn't. We'll come back to it. It's one of the few places where the beautiful first minute's recipe still has a smudge that nobody has quite cleaned up. But first, the helium. Because once the deuterium held, once that bottleneck opened, somewhere around 3 minutes in, the reactions didn't just begin politely. They ran. Deuterium absorbed a neutron and became helium-3. Helium-3 found another deuterium and became helium-4. 2 protons, 2 neutrons, bound together in one of the most stable small packages nature knows how to make. And the universe, in the space of the next several minutes, quietly turned a quarter of itself into helium. A quarter. Let that settle for a moment. Not a trace, not a percent or two, not some background whisper hiding in the corners. A full quarter of all the ordinary matter that would ever exist turned into helium in a span of minutes. By the time the universe was roughly 20 minutes old, it had already written one of the most important numbers in all of cosmology and then sealed it permanently into the fabric of everything. That number is called the helium mass fraction, and physicists write it today as approximately 0.247. You can think of it this way. If you could take all the ordinary matter in the universe, every proton, every neutron, every atom in every star and cloud and galaxy, and weigh it all on some impossibly vast scale, about a quarter of that weight would be helium. About 3/4 would be hydrogen. Everything else, all the carbon, oxygen, iron, silicon, gold, calcium in your bones, the nitrogen in each breath you're taking right now, all of it together amounts to a rounding error. A thin, precious dust on top of an overwhelming sea of 2 simple gases. 3/4 hydrogen. 1/4 helium. Those 2 numbers were set in the first few minutes of time, and they haven't changed in any dramatic way since. Now, there's a subtle thing worth noting, because it's the kind of detail that turns out to matter later. That 1/4 helium figure is by weight, by mass. If you count atoms instead, if you ask how many helium atoms there are for every hydrogen atom, the ratio looks very different. Because helium-4 is 4 times heavier than a hydrogen atom, that 25% by mass works out to only about 8% by count. Roughly 1 helium atom for every 12 hydrogen atoms. 12 to 1. a vast hydrogen majority, with helium a quiet, stable minority sitting alongside it, both made in those first minutes, both still here today in that same rough proportion, still drifting in the spaces between galaxies, still fueling stars, still waiting. And here is the thing that makes that number powerful. Not just that it's there, not just that it's measurable, but that you can predict it. From first principles. From nothing more than knowing the neutron to proton ratio at the moment nucleosynthesis began, you can sit down with a pencil and some nuclear physics and write down, before looking at a single star or a single gas cloud, what fraction of the universe ought to be helium. And you get roughly a quarter. Because of where things stood at around 1 second, that freeze-out we talked about earlier, 1 neutron for every 6 or 7 protons, almost every surviving neutron ended up inside a helium nucleus. That's the key. Neutrons can't just float around indefinitely. Left alone, a free neutron will decay in about 15 minutes, quietly transforming into a proton and releasing a couple of smaller particles along the way. So if you're going to make use of your neutrons, you have to put them somewhere safe. And the universe did exactly that. It tucked them into helium. 2 neutrons, 2 protons, bound together into helium-4. Extraordinarily stable, not going anywhere. If you start with 7 protons for every 1 neutron, and you package all the neutrons into helium, each helium nucleus needing exactly 2 neutrons, you end up using 2 protons in the process as well, and the math naturally yields a helium fraction close to 25%. It isn't a coincidence, it's arithmetic dressed up as astronomy. And that is one of the quietly astonishing things about Big Bang nucleosynthesis. The helium prediction is, in a sense, almost too easy. You don't need to know the fine details. You don't need to trace every reaction step by step. You just need to know where the neutron to proton ratio settled, and the helium fraction follows almost inevitably. The universe also made a little helium-3 along the way. Not much. A lighter, rarer version of helium, 2 protons and only 1 neutron rather than 2, produced in trace quantities during the same cascade of reactions. It's still out there, helium-3. Still detectable. Part of the same primordial record. But helium-4 was the dominant product. Helium-4 was what the universe was rushing toward, filling itself with, in those few productive minutes. After that, quiet, the reaction slowed, the temperature kept dropping. And the building of elements, the forge that had lit so briefly and burned so fast, went dark. Now, you might be wondering why it stopped where it did, why hydrogen and helium, and then essentially nothing. Why didn't the universe just keep going? It had the raw materials, protons, neutrons, helium nuclei. It had the heat, at least for a while. Why did the periodic table stall so completely after element number 2? The answer is beautiful and a little strange, and it comes in 2 parts. There's a reason built into the structure of atomic nuclei themselves, and there's a reason built into the nature of the expanding universe. Together they act like a double lock, and the universe hit them both at almost exactly the same moment. Let's start with the one built into the nuclei. To go from helium to anything heavier, you need a stepping stone, a rung on the ladder. After helium-4, 4 particles total, 2 protons and 2 neutrons, the next natural candidate would be an element with 5 particles. But there is no stable nucleus with exactly 5. Not one. No combination of protons and neutrons at that mass number holds together for any meaningful length of time. Nature simply doesn't offer a stable version of it. This is called the mass 5 gap, a missing rung. a place on the ladder where the ladder isn't. And if you try to skip it, if you try to take two helium-4 nuclei and fuse them together, you get beryllium-8. 8 particles total. 2 protons, 2 protons, 2 neutrons, 2 neutrons. Which sounds promising. But beryllium-8 is spectacularly unstable. It doesn't decay slowly. It doesn't linger for even a fraction of a second. It falls apart, splits right back into 2 helium-4 nuclei in less than a millionth of a billionth of a second. Less than 1 part in a quadrillion of a second. Think about that. If a second were the age of the universe, the lifetime of beryllium-8 would be, well, it wouldn't register. It wouldn't even begin to register. It's one of the most ephemeral things in nature. You make it, and it's already gone before the concept of gone has time to form. That's the mass 8 gap. Another missing rung. So here you have the young universe, trying to climb from helium to something heavier. Step 5 doesn't exist. Step 8 disintegrates before you can stand on it. The ladder has 2 consecutive gaps, one right after the other, and the early universe simply could not leap over both of them in the time available. Now, you might have heard, that stars manage to make carbon anyway. That stars fuse helium into carbon all the time, and they've been doing it for billions of years. How do they get around this problem? They use a trick that the early universe simply didn't have the conditions for. Inside a star, the density is enormous. The temperature is maintained for millions of years. And in those conditions, something remarkable can occasionally happen. 3 helium-4 nuclei come together almost simultaneously, not one by one, building up through an unstable intermediate, but very nearly all at once. 2 helium nuclei collide and briefly form beryllium-8 before it falls apart, and in that tiny sliver of time, in that window of less than a millionth of a billionth of a second, a third helium nucleus crashes into it, and instead of falling apart, the whole thing clicks into a carbon-12 nucleus. 12 particles, 6 protons, 6 neutrons, stable, permanent. This is called the triple alpha process, because a helium-4 nucleus is also known as an alpha particle. And it is genuinely one of the more miraculous accidents of physics. The fact that the energy levels of carbon-12 are arranged in just the right way to make this process possible. Fred Hoyle actually predicted, before it was measured, that carbon-12 had to have a certain energy level, because if it didn't, no carbon would exist, and neither would we. And when physicists looked, the level was there, exactly where it needed to be. But the triple alpha process requires extraordinary density and extreme patience. Stars have millions of years inside their cores. The early universe had minutes. And even if you could somehow bridge the gaps, even if beryllium-8 had been more cooperative, there was still the second lock. The expanding universe itself. Because as space expanded, it thinned. The particles that had been crowded together closely enough to collide, to fuse, to build something new, they were being gently pulled apart with every passing moment. Not dramatically, not violently, just steadily, the way a crowd slowly spreads out when a party is over and people start wandering home. By about 20 minutes after the beginning, the universe had cooled enough and spread enough that the nuclear reactions simply couldn't sustain themselves anymore. The fuel was still there, hydrogen everywhere, helium, a few lighter fragments. But the fire wouldn't catch. The temperature had fallen too far, the density had dropped too low, and that was that. The forge closed. Not with a bang. Not with any particular announcement, just a gradual, quiet dimming, the way an ember loses its glow without any ceremony. And when it was over, the recipe was fixed. 3/4 hydrogen, 1/4 helium, a thin whisper of lighter trace elements. That was what the universe had made, and that was what it would work with for the next several 100 million years, until the first stars lit up and the real chemistry began. There is something strangely peaceful about that, if you let yourself feel it. The universe didn't try to force more than it could make. It built what the physics allowed in the time the physics permitted, and then it waited. Patiently, for hundreds of millions of years, just that warm fog of hydrogen and helium drifting through the dark, slowly gathering under gravity, growing denser in some places, thinner in others, on its way toward becoming stars. But we're getting ahead of the story, because there was one more element made in those minutes. Not in large quantities, not in the dramatic rush of helium formation, but made, nonetheless, in vanishingly small amounts. Lithium, element number 3. The lightest metal, the element that sits at the top left corner of the periodic table's main body, just below hydrogen and helium in atomic number. And in the first few minutes of the universe, it was created, barely, faintly, in amounts so small that the counting of them requires extraordinary precision just to confirm they're there at all. The number is something like a few atoms of lithium-7 for every 10 billion atoms of hydrogen. Not per million, per 10 billion. If you took 10 billion hydrogen atoms and spread them out, you'd find, hiding among them, somewhere a handful of lithium atoms. 3, perhaps 4. That's how thin the primordial lithium was. And yet, it was made. The same chain of reactions that produced helium, running at the edges of its productive window, also managed to assemble a tiny fraction of lithium-7. 2 protons, 4 neutrons, locked into a stable nucleus that would outlast those early minutes and drift forward into the history of the universe. Much of that lithium-7 didn't arrive directly, though some of it came by a quieter route. During the same reactions, the universe made a small amount of beryllium-7, a nucleus with 4 protons and 3 neutrons. Beryllium-7 is radioactive, but slowly. It decays with a half-life of about 53 days, which in cosmic terms is almost instantaneous, but which is still long enough to carry it forward from the first few minutes into the slightly cooler universe that followed. And when beryllium-7 decays, it captures an electron and quietly becomes lithium-7. So some of the lithium-7 we're looking for was actually born as beryllium-7 and only revealed itself later. Delayed lithium arriving on a gentle detour. All of that was predicted. It was worked out in painstaking detail as part of Big Bang nucleosynthesis, the same framework that predicted the helium, the deuterium, the helium-3. And for most of those elements, when astronomers went and looked, they found what the theory said they'd find. But with lithium, something odd happened. The story of the cosmological lithium problem is one of the more quietly intriguing puzzles in modern cosmology. Not a crisis, not an emergency, more like a polite but persistent question that keeps raising its hand in the back of the room, even after everyone else has sat down. Here's the situation. When physicists run the Big Bang nucleosynthesis calculation, when they feed in the known constants, the neutron lifetime, the baryon to photon ratio, the nuclear reaction rates, and ask how much lithium-7 should have been produced, they get a number, a clear prediction. And then astronomers go looking for that amount of lithium in the oldest, most pristine stars they can find, stars born close to the beginning of the galaxy, before most of the later chemistry happened, and they find less. Not a little less. About 3 times less. 3 times. For decades, astronomers found that the oldest stars, the ones with the least contamination from later star formation, all seemed to have about the same amount of lithium, a flat plateau, reassuringly consistent, which at first seemed like a good sign, a real signal, not noise. This plateau is sometimes called the Spite Plateau, named after Francois and Monique Spite, who identified it in the early 1980s. The problem is that the plateau is in the wrong place. It sits at about a third of where the Big Bang theory says it ought to be. Now, there are ways to interpret this. The discrepancy doesn't mean the theory is wrong. Big Bang nucleosynthesis is otherwise spectacularly successful. The deuterium, the helium, the helium-3 all agree with predictions to impressive precision. Lithium is the outlier, the one ingredient in the recipe that doesn't quite line up. Some scientists have suggested that the lithium simply got destroyed. Stars are not static objects. They churn, they mix, they cycle material through regions of different temperature. And lithium is, in cosmic terms, a fragile element. It burns in stellar interiors at temperatures far lower than what destroys most other things. If lithium drifted down into the hotter interior of an ancient star, it could have been quietly consumed, leaving the surface, which is all we can observe, depleted. In that reading, the primordial lithium was there. We just can't see it anymore, because the stars swallowed it. Others have suggested something more intriguing, that the discrepancy might be a hint of physics we haven't found yet. Some unknown particle, some process that operated in the early universe and depleted the lithium before the first stars even formed. The window between nucleosynthesis and the birth of the first stars is not perfectly understood, and there could be something happening in that gap that the standard model doesn't account for. Neither explanation has been confirmed, neither has been ruled out. The cosmological lithium problem sits gently at the edge of our understanding, not as evidence that the Big Bang didn't happen, not as a challenge to Beban, but as a remaining question mark, a reminder that the universe still has a few things it hasn't finished telling us. And there is something rather lovely about that, if you think about it from the quiet of wherever you are right now. The fact that we can say, with confidence, here is one small place where the numbers don't quite match, and here are the 2 or 3 most reasonable explanations, and we are still working it out. That is not a failure. That is how science actually works, at its best. An almost complete picture, with one corner of the puzzle still face down on the table. The lithium-7 is out there, in ancient stars, in the oldest gas clouds, in quantities we can detect and measure and argue about. 3 atoms per 10 billion, give or take the factor of 3. A cosmic trace, a thin thread of element number 3 woven into the universe's opening chapter. And that, more or less, is where the first minutes left things. Hydrogen, helium, a thin whisper of lithium, and a trace of deuterium and helium-3 for good measure. 4 elements, well, 3 elements and 1 isotope, produced in a window of a few minutes, and then the door closed, and the universe spread out into the dark with its simple cargo, patient, cooling, waiting for the next chapter to begin. You could think of those first minutes as the universe's rough draft, a single paragraph written in fire, compressed into almost nothing, containing almost everything that would eventually become you. Not in form, not yet, but in raw material, the hydrogen that would one day be water, the helium that would one day float in balloons at birthday parties, the trace elements that would one day become the first stars. All of it assembled, all of it sealed, in a window of time so brief that it almost seems impossible. And yet it happened. We know it happened because the evidence is still here, 14 billion years later, waiting to be read. The helium fraction we measure in ancient, pristine galaxies, galaxies far away, chemically simple, barely touched by later stellar evolution, matches the prediction from Big Bang nuclear synthesis to within about 1%. 1%. Think about what that means. A theory about the first 3 minutes of time, tested by looking at light that has travelled for billions of years, matches what we observe to within 1%. The deuterium we measure in ancient intergalactic gas clouds, clouds so old and undisturbed, they're as close as we can get to reading the recipe in its original form, matches the theory as well, beautifully, and in matching tells us the amount of ordinary matter the universe contains. These aren't coincidences. They're a fingerprint. And they're the fingerprint of those 3 minutes. Somewhere, right now, in the glass of water on your nightstand, in the steam from the kettle you might have had before bed, in the moisture in the air you're breathing, there are hydrogen atoms that are almost 14 billion years old. They were made in those first minutes. They were never remade. They have not been altered in any meaningful way. They drifted through the cooling universe, gathered into gas clouds, fell into stars, were expelled when the stars died, gathered again into planets, poured into oceans, rose into the air, fell as rain, and eventually found their way to you. To the glass, to the nightstand, to this moment, right now. The hydrogen that makes up 2/3 of every water molecule you'll ever drink was forged before the first star lit up, before galaxies existed, before the universe was even a few minutes old. That's not a metaphor, it's a measurement. The helium is there too, quietly mixed in wherever it found itself, in stars, in the spaces between, in tiny pockets trapped deep in the earth. The lithium, if you look carefully enough in the right places. All of it originating in those few minutes, all of it still here, patient and unchanged in its fundamental nature, drifting through 14 billion years to arrive at this particular moment, this particular darkness, wherever you are. The universe wrote its opening recipe in 3 minutes. And you're made of it, not metaphorically, not approximately. You are made of the direct products of those first few minutes. The hydrogen in your body, the water in your cells, the simplest atoms that everything else was eventually built on. The heavier stuff, the carbon, the oxygen, the iron, that came later, from stars. But the foundation, the majority by weight of every atom in you, that foundation came from the beginning. The forge closed after about 20 minutes. The mass 5 and mass 8 gaps saw to that. The spreading, thinning universe saw to that. And the result, that quiet, almost nothing inventory of elements, is what the cosmos handed to the first stars when they finally formed, hundreds of millions of years later. The stars took hydrogen and helium and built everything else. Carbon and oxygen and iron and gold, element by element, in their cores, over millions and billions of years. And when stars died, in supernovae, in slower expirations, in the soft shedding of their outer layers, they scattered those heavier elements back into the universe, into new gas clouds, into new stars, eventually into planets and oceans and air and living things. But all of that came after. All of that is a later chapter, a downstream story, a long elaboration on a very simple opening sentence. The opening sentence was hydrogen and helium. 3 minutes in, the sentence was already written. And the universe has been building on it ever since, slowly, patiently, for nearly 14 billion years. The last thing made in those first minutes was also the rarest, lithium-7, arriving partly through beryllium-7's quiet transformation, sitting now in ancient stars at 1/3 of the expected abundance, still puzzling the people who measure it. A small mystery, a gentle one. Not a problem, not a failure, but a question mark held lightly at the edge of a very large, very successful understanding. The cosmological lithium problem is, in some ways, the most human part of this whole story. The universe made something, and we can almost count it, but not quite, and we're not entirely sure whether the stars hid it from us or whether something deeper is going on. We have two reasonable guesses and an open debate, and that debate is not anxious or urgent, it's careful, methodical, the way science is when it's working well. In the meantime, the rest of the recipe holds. The deuterium, the helium, the hydrogen, all of it consistent with the theory, all of it confirming that something real and measurable happened in those first minutes, something that left its fingerprint in the oldest things we can observe. 3 elements, 1 window, 3 minutes, and the universe has been using that starting kit ever since. Helium came quickly once the door opened. Deuterium had been the bottleneck, the essential first step, and once it could finally hold together, the reactions moved with something like urgency. Within minutes, most of the deuterium was gone, consumed, converted into something more permanent. Helium-4, 2 protons, 2 neutrons, locked together so tightly that almost nothing in the early universe could break them apart again. And the neutrons, the careful survivors, the ones that had made it through the freeze out without decaying, almost all of them ended up inside a helium nucleus, sheltered there, stable, done wandering. That sheltering is why the helium fraction is what it is. Start with a ratio of 1 neutron for every 7 protons. Lock almost every neutron safely into helium-4. Do the arithmetic slowly, the way you might count something on a quiet evening, and you arrive at a number very close to 25%. Roughly a quarter of all the ordinary matter in the universe, by weight, became helium in those first few minutes. Cosmologists write it as a decimal, 0.247, which looks precise and a little cold on paper. But what it means, in plain terms, is that for every 4 kilograms of ordinary matter anywhere in the cosmos, 1 of those kilograms became helium. The other 3 stayed as hydrogen. Now, weight and count don't always say the same thing. Helium is 4 times heavier than a single hydrogen atom, which means that 25% by mass is only about 8% by count. Out of every 100 atoms drifting through the early universe, roughly 8 were helium and 92 were hydrogen. 12 hydrogen atoms for every 1 helium atom. 12 to 1. That ratio, that quiet arithmetical consequence of the neutron to proton freeze out, is still the ratio astronomers find when they look at the oldest and most unprocessed gas in the observable universe. Pristine clouds, barely touched by later stars, still holding the original mixture almost unchanged. The recipe from those first minutes, written once and kept. There was also a smaller amount of helium-3, the lighter sibling, 2 protons and only 1 neutron instead of 2. A trace, far less than helium-4, but present and measurable and consistent with the theory. The universe kept its notes. And then the universe ran out of road. Not because anything failed, not because the reactions stumbled, but because the periodic table, it turns out, has 2 steps that are simply missing. 2 rungs in a ladder that aren't there. No nucleus with a combined weight of 5 is stable. Build one, and it falls apart before any instrument can register it, before any clock can tick. The same is true for a combined weight of 8. Beryllium-8, the particle that would form naturally when 2 helium nuclei come together, disintegrates in less than a millionth of a billionth of a second. Far less than that, actually, something like 10 to the power of minus 16 seconds. It exists for an instant so brief it doesn't really exist at all in any practical sense. Those two gaps, the mass 5 gap and the mass 8 gap, are not early imperfections, they are features of how the strong force happens to work. And in the young universe, they were walls. Helium could not climb into anything heavier because the very next natural step dissolved the moment it formed. Deep inside stars, billions of years later, there is a way around this. 3 helium nuclei can fuse almost simultaneously, 3 at once, in a rare but real 3-body collision that happens often enough inside the enormous pressures at a stellar core to leap over both gaps in a single bound. Carbon is the result. This is called the triple alpha process, and it is how the universe eventually found its detour. It is where the carbon in every living thing on Earth came from, much later, in the hearts of stars not yet born. But the early universe had no stars, it had expansion, cooling, and a clock running down. Within about 20 minutes of the beginning, the temperature had fallen too far, and the density had thinned too much. Not enough particles close enough together. Not enough energy to push through the reactions. The nuclear fire that had briefly burned across all of space simply slowed and quieted and stopped. Not with any drama, more like a fire burning down to coals when the wood is gone, until even the coals go dark. The cosmic kitchen closed, and what was left in the bowls at that moment was what everything in the universe would have to work with. So there was lithium, that faint final syllable of the first minutes, present in quantities so small they are almost poetic. A few atoms for every 10 billion atoms of hydrogen, not a rounding error in a larger number. That is the actual fraction, vanishingly small, arrived partly in disguise. Much of what is now lithium-7 began its existence as beryllium-7, an unstable nucleus formed in those closing moments that then quietly decayed over the weeks and months that followed, becoming lithium after the fact. A slow delivery, the universe leaving something in the post. And that lithium, measured in the oldest metal-poor stars, in gas clouds nearly untouched since the beginning, that lithium is about a third of what the equations say it should be. The theory predicts roughly 3 times as much. Astronomers look carefully, measure patiently, and find only a fraction of what Big Bang nucleosynthesis expects. The cosmological lithium problem has been sitting in the scientific literature for decades now. Not resolved, not forgotten. Just open, held quietly at the edge of an otherwise extraordinarily successful theory. Maybe the old stars processed some of the lithium away over their long lifetimes. Maybe there is something subtle in the nuclear physics not yet fully pinned down. Maybe the measurements themselves carry an uncertainty not yet traced to its source. Nobody is sure, and nobody is especially alarmed. The rest of the recipe, the hydrogen, the helium, the deuterium, holds with a precision that is, by any measure, remarkable. Lithium sits a little shy of its predicted value, and the people who study it are patient, careful people who understand that some questions take a long time to answer. That kind of patience in science is not a weakness, so let's stay with that patience for a moment, because it leads somewhere. The lithium problem is the one wrinkle in an otherwise extraordinarily clean result, and to appreciate just how clean that result is, it helps to step back and look at the whole picture. The full recipe, laid out the way a physicist would, with all 4 ingredients side by side, and the theory holding them together. Big Bang nucleosynthesis. That is the formal name for what we have been gently walking through tonight. Scientists abbreviate it BBN, and they say those three letters with a particular kind of confidence. The confidence that comes not from hope, but from decades of measurements that kept agreeing with each other when they had no obligation to. Mobilin is one of the three great pillars of the Big Bang theory. Not a footnote, not a supporting detail, a pillar. One of the three main reasons cosmologists believe the Big Bang really happened, that the universe really did begin in a hot, dense fireball that expanded and cooled, that the first minutes really were as strange and specific as the equations say. The other two pillars are the expansion of the universe, galaxies drifting apart, first noticed by Edwin Hubble in the late 1920s, and the cosmic microwave background, that faint, even glow of heat left over from the early universe. Detectable in every direction you point a sensitive antenna. We will come to that second one shortly. It has its own quiet story. But BBN stands on its own. And the reason it is so convincing is this: the entire set of predictions, how much hydrogen, how much helium, how much deuterium, how much lithium, all depend on a single number. One number. And that number can be measured two completely different ways, using completely different telescopes, looking at completely different things, and they agree. That number has a name. It is the baryon to photon ratio. Baryons are the technical term for the ordinary particles of matter, protons, neutrons, and anything built from them. When scientists say ordinary matter, they mean baryons. Everything you can see, touch, weigh, or bump into is made of them. Photons are particles of light, and the baryon to photon ratio is simply the number that answers this question. For every particle of ordinary matter in the universe, how many particles of light are there? The answer is lopsided in a way that takes a moment to absorb. For every single baryon, every proton, every neutron, there are roughly 1.5 billion photons. Written the other way, for every 10 billion photons, there are about 6 ordinary matter particles. 6 per 10 billion. That is not a typo. That is the actual balance of the universe. Matter is a thin minority, swimming in a sea of light so vast that matter barely registers against it by count. Right now, wherever you are surrounded by light from the early universe, not visible, too faint and cold, but present in every direction, outnumbering you at a ratio that is essentially incomprehensible. And yet that absurdly lopsided ratio is precisely what the BBN equations use as their single input. Feed it in on one end. The calculations run. The temperatures, the freeze-outs, the bottlenecks, the cascade into helium. And out the other end come the predicted abundances of hydrogen, helium, deuterium, and lithium, all 4 at once. Then you go look. You find pristine gas clouds billions of light-years away, gas that has sat nearly undisturbed since very early in the universe's history, barely contaminated by the exhaust of later stars. You measure the helium, you measure the deuterium, you measure the ratio, and it agrees with what the equations said it should be. Not approximately, not in the right neighborhood. It agrees at the level of a few percent or better, which in cosmology is a kind of precision that earns its own quiet round of applause. The helium fraction in the oldest, most chemically pristine galaxies astronomers can find, galaxies poor in heavy elements, barely touched by generations of stellar burning, agrees with the Big Bang prediction to within about 1%. 1%. For a number calculated from the physics of the first 3 minutes, confirmed by telescopes pointed at galaxies billions of light-years away, measuring material billions of years old. That is not luck. That is a theory that was right. And deuterium is where the measurement becomes especially pointed. Remember the deuterium bottleneck, the way the light was so intense and numerous in those first minutes that it kept shattering every deuteron the instant one formed. The reason it shattered so efficiently was not because the individual photons were especially powerful, it was simply that there were so many of them, over 1 billion for every atom. Sheer numbers, overwhelming every attempt at assembly. That sensitivity cuts both ways. Because deuterium's survival depended so delicately on how many photons were pressing against it, the amount of leftover deuterium is exquisitely sensitive to that baryon-to-photon ratio. A small change in the amount of ordinary matter in the universe, a slight increase in the baryon count, and more deuterium would have been processed away, burned into helium, leaving less. A slight decrease, and more would have survived. Deuterium is a precision scale, a set of cosmic weighing plates, balanced at the very beginning of time. So when astronomers find those ancient, pristine gas clouds, the ones nearly untouched since the early universe, and measure the deuterium there, they are not just observing an element, they are weighing the ordinary matter of the entire cosmos, the whole sum of it, in one careful observation. And that measurement agrees with the helium, with the Beban prediction, with the baryon-to-photon ratio calculated entirely independently from the patterns in the cosmic microwave background, that faint afterglow of heat from hundreds of thousands of years after the first minutes. The same number from 2 different clocks, 2 different cosmic records, 2 different centuries of observation. That is why Babylon earns its place as a pillar. 3 of the 4 predictions hold beautifully. Hydrogen, helium, deuterium, measured, confirmed, consistent. Lithium sits a little low, and the patient people are still working on it. But 3 out of 4, with a precision like that, is not a near miss. It is a triumph. Now, before we go any further into what all of this means, it seems right to spend a quiet moment with the people who figured it out. Because the story of how anyone came to understand what happened in the first 3 minutes is itself a gentle kind of marvel. It did not begin in a laboratory. It began with an equation, a joke, and a prediction that was ignored for 17 years. It was the 1940s. The war had only recently ended. George Gamow, a Ukrainian-American physicist with an enormous personality and an enormous talent for translating ideas between the abstract and the vivid, had been thinking about the early universe. He believed the elements had been cooked in the primordial fireball, that the heat at the beginning was so intense it could have run nuclear reactions on a cosmic scale. His young graduate student was Ralph Alpha. Alpha did the hard mathematical work, calculating how the early universe might have produced the elements, how the reactions would have proceeded as the temperature fell, what abundances would have been left behind. The resulting paper was published in 1948. Physical Review, and it was signed, as its authors, by Alpha, Bethe, and Gamow. Hans Bethe had not actually written the paper. Gamow, irrepressible as always, had added his name anyway, because with Alpha, Bethe, and Gamow, the authors' names sounded like the first 3 letters of the Greek alphabet. Alpha, Beta, Gamma. It was too perfect to resist. Hans Bethe, a Nobel laureate and one of the most distinguished physicists alive, learned he was a co-author of the paper around the time it was published. He was reportedly amused. The paper became known as the alpha-beta-gamma paper, or the paper. It is one of the most famous author lists in the history of physics for reasons entirely unrelated to the science, and one of the most consequential papers in the history of cosmology for reasons entirely to do with it. But gamma and alpha did not stop there. In that same year, 1948, Alpha and a colleague named Robert Herman worked out something remarkable. If the universe had been hot and dense at the beginning, and if it had been expanding and cooling ever since, then that ancient heat should not have simply vanished. It should still be there, thinned and stretched by the expansion, cooled by 14 billion years of spreading out, but present. A kind of fossil warmth permeating all of space. They calculated what temperature it should be now. Their estimate, around 5 degrees above absolute zero. Absolute zero is the coldest possible temperature, the point at which thermal energy reaches its minimum. 5 degrees above that is extraordinarily cold, far colder than anything in your room, far colder than the surface of Pluto, but not zero, not nothing. A faint, detectable glow spread uniformly across the whole sky in every direction. The prediction was published. And then, more or less, it was set aside. The community was not fully ready for it. The idea of an expanding, cooling universe was still contested. Fred Hoyle, the same Fred Hoyle who had named the Big Bang skeptically on the BBC in 1949, who doubted the very theory he had inadvertently christened, was advocating for a steady-state universe with no beginning, and he had many thoughtful allies. So the prediction of Alpha and Herman sat in the literature, mostly uncited, for the better part of 2 decades. And then, in 1965 in New Jersey, 2 radio engineers named Arno Penzias and Robert Wilson were trying to use a large horn-shaped antenna, originally built for satellite communications, to make precise measurements of radio waves from the sky. They kept picking up a noise. Not from any source they could identify. Not from the city, or from any satellite, or from the galaxy. An even, stubborn hiss in their receiver, coming equally from every direction, constant whether they pointed the antenna at the ground, or the horizon, or straight up into space. They checked the equipment. They checked it again. They found, famously, that a pair of pigeons had been nesting inside the antenna, and had left a residue that Penzias and Wilson described, with commendable restraint in their paper, as white dielectric material. They cleaned the antenna. The hiss remained. They reached out to colleagues at Princeton, who had been independently working on the theory and planning their own search for exactly this kind of signal. The conversations that followed were brief. The hiss was the cosmic microwave background, the actual, measurable, detectable remnant of the early universe's heat, the fossil warmth that Alpha and Herman had predicted 17 years earlier. Penzias and Wilson received the Nobel Prize in Physics in 1978. The temperature of that background, that faint, even glow of microwaves coming from every direction in the sky, is 2.725 degrees above absolute zero. Not 5 degrees, as the early estimate had it, but remarkably close for a back-of-the-envelope calculation made in 1948 about events that occurred 14 billion years ago, 2,725 Kelvin. Measured today by satellites carrying instruments of extraordinary delicacy. The leftover warmth from the fireball of the beginning, stretched by the expansion of the universe into long, slow microwaves, detectable in every direction you can look. It is one of the most beautiful numbers in all of science, a number that says, yes, there was a beginning, and it was warm. Now, while we are sitting quietly with the people in this story, it is worth noting the other half of the picture, the half that explains why the universe did not stop at helium. In 1957, a paper was published that has become famous under a shorthand that matches its authors, B²FH, Hoyle, Fowler, and the husband and wife team of Geoffrey and Margaret Burbidge. 4 people. 1 paper. The title, in full, was Synthesis of the Elements in Stars. What Hoyle and his co-authors showed, in comprehensive, rigorous, beautiful detail, was that nearly all the elements heavier than helium are made not in the Big Bang, but inside stars. Carbon, oxygen, neon, silicon, iron, assembled over millions or billions of years in stellar cores, in the extreme pressures and temperatures at the hearts of massive suns, and then scattered into space when those stars exploded at the ends of their lives. It is a different chapter of the same story. The Big Bang wrote the opening. Hydrogen, helium, a whisper of lithium. The stars took it from there, patiently transmuting across cosmic time, that simple starting kit into the full periodic table. Together, Bunn and the Burbidge-Fowler-Hoyle paper divide all of chemistry between them. The lightest things from the beginning. Everything heavier from the long lives and spectacular deaths of stars. Steven Weinberg brought all of this together for a general audience in his 1977 book, The First 3 Minutes. It is, by most accounts, one of the finest works of popular physics ever written, precise and moving at the same time. A book that takes the abstract machinery of the early universe, the equations, the thresholds, the cascades, and makes the reader feel the weight of what actually happened. The title itself is the clock we have been listening to all night. Now let's come back to that clock, because there is a kind of quiet poetry in the numbers themselves, if you let yourself hear it. At 1 second after the beginning, the universe was roughly 10 billion degrees. 10 billion. 10 followed by 9 zeros. Hotter than the core of any star alive today. Hotter than anything that currently exists anywhere in the known universe, except in the most violent of conditions. And yet already at 1 second, it was cooling. The expansion was doing what it always does, steadily, patiently, spreading the heat thinner across a growing volume of space. By 3 minutes, it had dropped to about 1 billion degrees. 1 billion. Still incomprehensible by ordinary standards. Still hot enough to run the nuclear reactions that built the helium. Just cool enough, finally, to let deuterium hold itself together long enough to matter. That is the entire cooking window, from 1 second to roughly 20 minutes. In those 20 minutes, most of what would ever be made in those first minutes was made. And by the end of those 20 minutes, the temperature had fallen far enough that the reactions simply stopped. Not because the fuel ran out. Because space had spread the fuel too thin, the fire needed proximity. And the universe kept expanding, kept cooling, kept carrying particles away from each other until the chance of a collision that mattered became too rare to count on. And then the fire went out. The universe settled into a long cooling. Still hot, still incandescently hot, in a way that human language struggles to describe properly, but no longer hot enough for nucleosynthesis. The recipe was locked, the ratios were fixed, and the cooling continued for a very long time. For about 380,000 years, the universe was still too hot for atoms to hold together. The electrons, which had survived the electron-positron annihilation, the ones that were not consumed in that last great flash, were still flying free, too energetic to be captured by any nucleus. The hydrogen nuclei and helium nuclei drifted in a sea of loose electrons and radiation. Then that changed too. About 380,000 years in, the temperature fell far enough that electrons could settle into orbits. Atoms formed. And the universe, which had been opaque, a dense fog through which light could not travel freely, suddenly went transparent. The light that had been trapped in that fog was released all at once, flooding outward in every direction. 14 billion years later, that same light, stretched and cooled by the expansion into microwave radiation into the 2.725-degree background, is the hiss that Penzias and Wilson found in their antenna. From 10 billion degrees to 2.725 degrees, from the first second to today, nearly 14 billion years of cooling spread across all of space, measured now in a number that has 3 digits after the decimal point and fits comfortably in a sentence. The universe has cooled, gently and continuously, for almost as long as time has existed. And yet it is not cold in any way that erases the record. The record is still there, encoded in the cosmic microwave background, in the ratios of light elements in ancient gas clouds, in the helium fraction in old stars. The first 3 minutes left fingerprints that the universe has been quietly carrying for 14 billion years. Let's slow down now. Let's let the pace soften even a little more, because we are coming to the part of the night where it is worth just sitting with what all of this means for you, here, in the dark, wherever you are. Nearly every hydrogen atom in existence was made in those first 3 minutes and has never been remade since. That sentence is worth holding for a moment. Hydrogen, the most common element in the universe, the fuel of stars. The lighter of the 2 atoms in every molecule of water was forged in the fireball of the beginning. Not in stars, not in supernova explosions, not in any process that has happened since. Stars destroy hydrogen, burning it into helium in their cores. But they do not make new hydrogen. The hydrogen they consume is hydrogen that was already there, all of it, made in the first 3 minutes, and then left alone. Think about the glass of water on your nightstand, if there is one, or the water in a glass you drank from earlier. Each molecule of water is 2 hydrogen atoms and 1 oxygen atom. The oxygen came from a star, a massive star that lived and died billions of years ago, fusing elements in its core and scattering them into space when it exploded. The oxygen is a few billion years old, perhaps, but the hydrogen, the 2 hydrogen atoms in each molecule of water you drink, are nearly 14 billion years old, forged before the first star ever shone, before galaxies formed, before the universe was even transparent. Those 2 small atoms have been drifting through the cosmos since nearly the beginning, through gas clouds, into stars, out again into the interstellar medium through billions of years of cosmic recycling, and now they are here, in a glass, in the dark, near where you are sleeping. That is not a metaphor. That is what the physics says. The hydrogen in water is a genuine, direct, physical relic of the first 3 minutes. The universe that existed 3 minutes after its own beginning is, in that specific and concrete sense, present in your room tonight. If that is not a reason for a kind of quiet awe, it is hard to know what would be. And it is not just the water. When you look up at the helium fraction of the universe, the roughly 1/4 of all ordinary matter, by weight, that exists as helium, you are looking at a number that was written in those first minutes and has barely changed since. All the stars in all of history, burning hydrogen into helium for billions of years, have shifted that fraction by only a small amount. A few % of the original hydrogen has been converted into heavier things, all the carbon, all the oxygen, all the iron and gold, and calcium and sulfur. The entire contents of the periodic table beyond lithium, that all came from stellar processing. But the total amount of hydrogen converted is modest. Surprisingly modest. 3/4 of all the ordinary matter in the universe is still hydrogen. Still the original, unchanged product of the first 3 minutes. The cosmos spent 14 billion years building stars and galaxies and planets and you. And when you add it all up, the raw material is still mostly the same as it was when the fire went out. The universe is still, in the deepest sense, the universe of its first few minutes. Everything else, the carbon in your cells, the iron in your blood, the calcium in your bones, is the thin, precious garnish that billions of years of stellar chemistry added on top. That hydrogen fueling the sun right now, driving the reactions in the solar core, keeping the light on, warming your atmosphere, was created in the first 3 minutes and has simply been waiting, patiently, in one form or another, ever since. It did not know it was going to become the sun's fuel. It did not know anything. It was just hydrogen, the simplest thing, drifting through an expanding universe, waiting for gravity to gather it. And then gravity gathered it. Now think about the carbon. Every carbon atom in your body was once, in a very real sense, impossible to make. Not impossible as in unlikely. Impossible as in the physics of the first 3 minutes made no path from helium to carbon available. The mass 5 gap and the mass 8 gap were closed doors. Beryllium 8 fell apart before anything could build on it. The universe ran out of time before it ran out of helium. Carbon simply could not form in those first minutes, no matter how much helium was present. So the universe waited. Hundreds of millions of years passed. Hydrogen and helium gathered under gravity into great clouds, denser and denser, hotter and hotter at the core, until the pressure and temperature at the center became high enough to run the triple alpha process, the trick that lets 3 helium nuclei find each other simultaneously and fuse into carbon, leaping over the gap that the early universe could not cross. The stars figured out what the fireball could not. They had the time, and the density, and the patience. And so carbon exists. Which means you exist. Which means there is someone lying in the dark tonight, on this specific, unusual planet, made of atoms that the universe spent hundreds of millions of years learning how to forge. The first 3 minutes gave you the hydrogen. The stars gave you everything else. Both gifts were necessary. Here is another thing worth holding gently. Physicists today can take the equations of nuclear physics, the ones worked out in laboratories on Earth, measuring the same forces and reaction rates that were at work in the early universe, and run the entire first 3 minutes on a computer. A simulation of the cosmic cooking. Temperatures, densities, reaction rates, all advancing step by step through the first 20 minutes. And the simulation reproduces the observed abundances to within a few percent. A few percent. For a calculation of something that happened nearly 14 billion years ago. The neutron's lifetime, about 15 minutes. Measured today in laboratory experiments with beams of neutrons and careful clocks, when plugged into the equations, correctly predicts the helium fraction we measure in the sky. A number measured in a lab on Earth, describing a process from the first minutes of the universe. The same number. Consistent. The helium fraction, it turns out, is surprisingly robust. It does not depend sensitively on most of the fine details of the nuclear physics. It depends mostly on the neutron-to-proton ratio at freeze-out, that quiet 1:7 imbalance, and the neutron lifetime. Fix those two things, and the helium fraction follows almost automatically, which is part of why the prediction is so reliable. It does not rest on a fragile house of cards. It rests on the simplest possible physics. Count the neutrons, know the fraction. Deuterium, as we said, is different. Deuterium is the sensitive one, the canary. A small change in the baryon to photon ratio shifts the deuterium abundance significantly, far more than it shifts the helium. That sensitivity is what makes deuterium so valuable as a measurement tool, and it is why astronomers hunt so patiently for pristine gas clouds where the deuterium has been preserved nearly unchanged since those first minutes. When they find those clouds, ancient, metal poor, as close to the primordial composition as the universe still offers, and measure the deuterium there, they are reading the original document, the recipe as written. And one more thing the first minutes did, quietly, that tends to get overlooked. The abundances of the light elements constrain how many types of neutrino can exist. Neutrinos are one of the fundamental particles of nature, and for a long time, physicists wondered how many distinct varieties there might be. The answer, as it turns out, is three types, or three flavors, of neutrino, corresponding to the electron, the muon, and the tau. But how do we know? One of the ways we know is that the first 3 minutes put a limit on it. More types of neutrino would have changed the expansion rate at the time of freeze-out, which would have changed the neutron to proton ratio, which would have changed the helium abundance, which would not have matched what we measure. The helium in ancient stars, in pristine galaxies, quietly tells us that the number of neutrino types is 3. Not 4, not 5. 3. The first minutes of the universe constrain the particle physics of the present. That is not something most people know. And it is remarkable. Let's come to the oldest stars. In the disk of our own galaxy, in the halo of very old stars that formed long before the Milky Way fully assembled itself, there are stars that are poor in heavy elements. Astronomers call them metal poor, using the astronomers' convention that everything heavier than helium counts as a metal. These stars formed when the galaxy was young, from gas that had not yet been much enriched by generations of stellar burning, gas that was still close to the primordial composition. The helium fraction in those oldest stars, measured carefully, corrected for the small amount of helium the stars themselves have produced over their lifetimes, preserves a near-original record of the helium fraction from before the galaxy formed, and it agrees with the prediction, with the Beban calculation, with the baryon to photon ratio. The same picture holds in distant, chemically pristine galaxies. Galaxies caught in a state close to their original composition, their helium fraction measured by looking at the light they emit. Analyzed across the spectrum, the helium measured there agrees with the Big Bang prediction to within about 1%. 1% in a measurement spanning billions of light years and billions of years of cosmic history. The universe wrote its recipe in 3 minutes, and the recipe is still legible. Now we are near the end of our journey tonight, wherever you are. The fire that forged the first elements went out about 20 minutes after the beginning. The universe settled into a long, quiet cooling. Hydrogen and helium, in their roughly 3-to-1 ratio by mass, drifted slowly through expanding space. Neutrinos moved freely through everything, barely touching anything, a cold, invisible sea. Photons outnumbered baryons by 1,000,000,000 to 1, pressing against the matter in every direction, keeping atoms from forming for hundreds of thousands of years still to come. And then, slowly, the first structure began. Gravity. The faintest unevenness in the distribution of matter, a tiny fluctuation, a region just barely denser than its neighbours, began to pull, slowly, over millions of years. And then faster, as more matter fell toward the same place, great clouds of hydrogen and helium condensing under their own weight. Growing denser, growing hotter at the core, until the pressure and temperature at the center of a gas cloud reached a threshold that should feel familiar to you now. The temperature where nuclear reactions can run, where hydrogen nuclei can fuse, where the fire can start again. The first stars ignited, and with them the periodic table opened its pages past helium. Carbon, oxygen, neon, silicon, iron, the elements the first minutes could not make, assembled slowly and methodically inside stellar cores over millions and billions of years. Those stars lived, and then they died. They scattered the new elements into space, new clouds formed, enriched by that stellar exhaust, and new stars formed from those enriched clouds. Generation after generation, cycle after cycle, until, about 4.5 billion years ago, one such cloud, in one ordinary arm of one ordinary galaxy, collapsed to form a star of middling size, and around that star, a collection of leftover material assembled itself into planets. One of those planets, at the right distance from its star, developed liquid water and, in time, life. Life made of carbon and oxygen and iron and calcium, all forged in stars. Life watered by hydrogen, forged at the beginning of time. Life sustained by a star burning hydrogen, the oldest fuel in the universe that has been waiting since the first 3 minutes. You are the most elaborate thing the universe has yet made from its first 3 minutes. The hydrogen in you is ancient beyond ordinary imagining. The carbon was assembled in a stellar core that no longer exists. The oxygen was scattered through space by an explosion that happened billions of years before your sun was born. And yet here it all is, assembled into one warm, breathing, dreaming thing, lying in the dark, listening to a calm voice trying to help you sleep. The universe wrote its opening recipe in 3 minutes, spent a few 100 million years learning how to do chemistry, and has been elaborating on it ever since. Every star, every planet, every ocean, every living thing is the universe slowly exploring what can be made from hydrogen and helium and time. And the answer, it turns out, is everything. Earlier tonight, at the very beginning, we talked about the glass of water on your nightstand. The hydrogen in it was made before the first star. It is older than the Earth, older than the Sun, older than any planet or galaxy or structure you could name. It has been hydrogen since the first minutes, drifting through the vast dark spaces between galaxies, and now it is here. Near where you are resting, 14 billion years and 1 trillion miles from where it began. You started this night with that hydrogen. And the whole story we travelled through tonight, the quark-gluon plasma freezing into protons and neutrons, the great freeze out at 1 second, the deuterium bottleneck holding the door shut until the temperature fell enough. The cascade into helium that happened in just a few minutes, the mass 5 and mass 8 gaps closing the door on heavier elements, the 20-minute window ending and the fire going quietly out, all of it was always quietly present in that water, in the ordinary, unremarkable glass, in the 2 hydrogen atoms in each molecule, in the oldest things in your room. I hope that feels less like a physics lesson now and more like what it is, which is simply the story of where you are from. If you are still awake, and if so, that is entirely all right. Some nights the mind wants to rest in the questions before it rests in sleep. I want you to know that everything you heard tonight is real. Every number, every name, every threshold crossed, and every element forged. Ralph Alpha doing the hard mathematics in the 1940s. The stubborn hiss in Penzias and Wilson's antenna. The helium fraction, measured in a galaxy billions of light-years away, agreeing with an equation to within 1%. The universe left evidence. We read it, and it holds. And somewhere in that holding, in that agreement between the theory and the measurements, there is something that I find genuinely comforting. The universe has been patient. It started simply from rules that hold everywhere and always. It cooled slowly. It built the simplest things first. It waited for gravity to do its long work. It did not rush. And here we are, at the far end of all that patient work, lying in the dark, our bodies made of ancient hydrogen and stellar carbon. Our minds, for a few more quiet minutes, still turning over the questions. You don't need to hold on to any of the specific numbers. They'll be here when you wake. The deuterium bottleneck will still have broken at 1 billion degrees. The helium fraction will still be roughly 1/4. The hydrogen in your water will still be 14 billion years old. It will all still be true in the morning. Wherever you are listening from tonight, and whatever time it is in your corner of the world, I'd love to know. Leave a word or two in the comments if you feel like it. There is something quietly wonderful about the idea of people on different continents, in different time zones, all lying in the dark with the same ancient hydrogen nearby, listening to the same story. If Grandpa's Late Nights is a regular part of your evenings, a gentle like and subscribe means more than you might think. Small channels like this one run entirely on that support, and it is what keeps the porch light on for another night. Take a slow breath. Let the numbers soften into shapes. Let the shapes soften into warmth. The universe began in a brightness so complete that nothing could exist, and it has been quietly cooling and building and elaborating for nearly 14 billion years, and somewhere in that long, patient process it made you. That seems like a good thing to carry into sleep. Good night, kiddo. Grandpa'll leave the porch light on.